Right, here's the question again. Jun04, question 5, and here's a question again about state the meaning of the term EMF. So again, EMF is the energy changed to electrical energy per unit charge passing through the battery or power source. Part B, figure 5.1 shows a battery of internal resistance 0.5 ohms connected in series with a resistor of resistance 4 ohms. The current in the circuit is 2 amps. Calculate the EMF of the battery. So we know there from that, this is just like a little series circuit with a 0.5 ohm resistor and a 4 ohm resistor in series with each other. And therefore the total resistance in the battery is going to be equal to, just scanning a wee bit there, it's going to be equal to your 0.5 ohms, which is your internal resistance, plus your 4 ohms, and that gives you 4.5 ohms. And then you are going to calculate the EMF is equal to the current times the total resistance in the circuit, and that's going to be equal to 2 multiplied by 4.5, and so it's a 9 volt EMF. Part 2, calculate the potential difference between the terminals X and Y of the battery. And so you can see there that you have the battery and the 0.5 ohm resistor in series with it, and it's the internal resistance. So we're looking for the EMF, the potential difference across that. And so again, we're just going to use V is equal to IR. Now that is equal to the, if you have the potential difference here across this is going to be equal to that. So we're going to calculate the potential difference through the 4 ohm resistor to get that. And so we're going to multiply our current of 2 amps multiplied by our 4 ohm resistor gives you 8 volts. And that means that there's been 1 volt dropped across this 0.5 ohm resistor. So consider a charge of 1 coulomb passing through the battery from the negative terminal to the positive terminal. Find the net increase in the energy of the charge. And so E is equal to Q times V. The charge is 1 coulomb. And the PD across the battery we have worked out was 8 volts, and therefore it's going to increase in energy by 8 joules. And that's available to do something in the 4 ohm resistor then in the rest of the circuit. Part C, another battery has an EMF of 12 volts. I'll show you the diagram. And an internal resistance of 0.8 ohms. A load resistor of resistance 5 ohms is connected across this battery as shown. This circuit is to be altered by way of an addition of another resistor to this load to make the total power transferred to the adapted external circuit from the battery a maximum. So therefore you have to put in another resistor, and you want to find out where you're going to get the maximum power. Now to get the maximum power transfer, what you have to do is to have your total external resistance here equal to your total internal resistance, which is here, and therefore we need our total external resistance to be equal to 0.8 ohms. Now there's no way you can add a resistor in beside that to work that out, and therefore we're going to have to add another resistor in parallel. But first of all, we're going to just make sure that we get our maximum power, and just so we just do a wee simple calculation. You get maximum power transfer whenever the internal resistance R is equal to the external resistance, and therefore that's going to have to be equal to 0.8 ohms. And so we're just going to use P is equal to V squared over R, and that gives you 12 squared over 0.8, and that gives you an answer of 45 watts. And it's the next part of the question then, which we have to put in our new resistor to make this load here have an equivalent resistance of 0.8 ohms, and I'm just going to draw one in here. Okay, and it's going to have to go in parallel. So it has to go in parallel, and it goes in parallel with the 5 ohm resistor. And then it says calculate the resistance of the additional resistor. So we know that this whole thing here has to give us a resistance, a total resistance of 0.8 ohms. And therefore we're going to do our calculation as if we were adding up our resistors in parallel. So 1 over the total resistance is equal to 1 over the R that we don't know, plus 1 over 5. Therefore that's 1 over 0.8 is equal to 1 over R plus 1 over 5. So 1 over 0.8 is equal to, minus 1/5, it gives you 1 over R. So you can do this on the calculator. 1 over R comes out to be 21 over 20. 21 over 20. And then you have to turn it upside down, of course, and so R is equal to 20 over 21. And it comes out then as 0.95 ohms. Part 3, remember that the additional resistor has been connected so as to give maximum power transfer from the battery to the combination of the additional resistor and the 5 ohm resistor. Calculate the power dissipated in the 5 ohm resistor alone. So we just have to do a wee quick calculation to work out the voltage across the 5 ohm resistor. So what we now have is a 0.95 resistor in parallel with a 5 ohm resistor. 0.95 and 5 ohms. Scan it a wee bit. Therefore, if we just do a V equals IR calculation, we know that the in fact, it's maybe even a little bit easier than that. Yeah, it is easier than that because we know that the voltage across this combination, because the resistance of the load and the resistance of the little internal resistance are the same. That means both of them are going to get half of the voltage of the battery. So that's 6 volts and this is 6 volts. And so the voltage across our combination here is 6 volts. And then all we have to use is P is equal to V squared over R. And that gives you 6 squared divided by the resistance is 5. And that gives you an answer of 7.2 watts. Gives you an answer of 7.2 watts.